Ever since you were very young, you learned that like charges repel each other.
So when we take a closer look at the center of an atom, why don't the protons in the nucleus of the atom repel? For this observation, we can thank the strong force.
In particle physics, there are 4 fundamental forces: gravity, the weak nuclear force, electromagnetism, and the strong nuclear force, each responsible for different phenomena in the universe. The electromagnetic force, responsible for light, electricity, and magnetism, also causes protons to repel one another. The massless particle which carries this force is called the photon. The strong force, responsible for binding protons and neutrons together, also binds together the quarks that make up the protons and neutrons. Its massless force carrier is the gluon. The electromagnetic force is approximately 137 times weaker than the strong force, which is the strongest of the fundamental forces. No wonder the protons stay together despite proton-proton repulsion. Each proton and neutron has 3 main quarks called valence quarks. If we take a look at the standard model of particle physics, we can see that there are 6 quarks. So which quarks are inside the protons and neutrons? Well, all of these quarks can exist as virtual particles popping into and out of existence in the protons and neutrons. However, the 3 valence quarks are up and down quarks, each of which has an individual charge which adds to give the protons and neutrons their overall charge. In addition to having a certain charge, these quarks also have a special property called color, unrelated to these particles' actual color, but critical to describing quark-gluon interactions. The quarks can be one of 3 colors: red, blue, or green. The rule is that protons and neutrons must be color neutral. For this to happen, there must be 1 blue, green, and red quark inside each of them. These colorful quarks interact with each other through the emission and absorption of force-carrying gluons, which explains how the strong force acts on particles. Gluons also have this color property, which is why when gluons are exchanged between quarks, the quark's color changes to keep the protons or neutrons neutral. The best theory we have to describe strong force interactions with particles is called quantum chromodynamics. Because gluons have color, QCD predicts that gluons should be able to interact with each other and should be able to stick to each other to form a glue ball. However, scientists have yet to discover them. There are experiments such as the solenoidal tracker experiment and the panda experiment being conducted to detect glue balls. The problem physicists are having with detecting a glue ball is that they don't know a glue ball's mass or the particles it decays into. A real problem since physicists reverse engineer particle collisions by analyzing decayed particles and the mass energy in the accelerator after a collision to identify particles. Currently, there are 2 candidates for glue balls, the F01500 and the F01710. New mathematical calculations make it clear that the F01710 may be a glue ball, but more experimental evidence is still required. The discovery of the glue ball is critical in verifying the accuracy of QCD and the standard model of particle physics. If a glue ball doesn't turn up, we just might have to rethink everything we thought we understood. I've got a glue on, I've got a glue on, I've got a glue ball.